Hello, welcome. This is lecture 5. In this part of the lecture, we are going to discuss the arc length of a space curve. The length of a plane curve with parametric equations x equals f of t and y equals g of t over the interval a to b is defined as the limit of the lengths of the inscribed line segments as follows. L equals the integral over the interval a to b of the square root of the sum of the squares of the derivatives of the component functions f and g. The length of a space curve is defined exactly in the same way. Suppose the curve has the vector function r of t, whose components are given as f of t, g of t, h of t, with parametric equations x equals f of t, y equals g of t, and z equals h of t, where t is greater than or equal to a, but smaller or equal to b. And f prime, g prime, and h prime are continuous functions on the interval a to b. If the curve is traversed exactly once as t increases from a to b, as in the figure, then it can be shown that its length is given by the formula shown in equation 5.1.a. Since the parametric equation x equals f of t, y equals g of t, and z equals h of t, so we have x prime equals f prime of t. Here prime denotes the differentiation with respect to t. So the formula shown in equation 5.1.1a can also be put into the form 5.1.1b. Now, the formula in equation 5.1.1a can be put into more compact form. L equals the integral over a to b of the absolute value or the magnitude of the vector r prime of t with respect to t. Since r prime of t has the form so its magnitude is given by this formula. The quantity here in equation 5.1.1a is in fact the magnitude of the vector r prime. So the equation 5.1.1a takes a very simple form as shown in equation 5.1.2. Let's have a look at an example. Find the length of the arc of the circular helix with the vector function r of t with the component functions cosine of t, sine of t, and t. From the point with coordinates 1, 0, 0 to the point with coordinates 1, 0, 2 pi. Let's have a look at the solution. Since the derivative of the position vector r has component functions negative sine of t, cosine of t, and 1. These components are obtained from the vector function r by simply differentiating the component functions. And we have the magnitude of this r prime is the positive square root of the sum of the squares of the component functions, which simplifies to positive square root of 2. We also observe that the point 1, 0, 0 corresponds to the parameter value t equals 0. So r at 0 is the vector with components 1, 0, 0. Similarly, the point 1, 0, 2 pi corresponds to t value 2 pi. Therefore, the length of the arc from the point 1, 0, 0 to the point 1, 0, 2 pi is given by the parameter interval 0 to 2 pi. And the length L is equal to the integral of the magnitude of r prime over the interval 0 to 2 pi, which gives 2 times square root of 2 times pi. The arc length function. Now we suppose that C is a curve given by the vector function r of t with component functions f of t, g of t, h of t over the closed interval a to b, where r prime is continuous and C is traversed exactly once as t increases from a to b. We define its arc length function s by the integral shown in equation 5.1.3. Where u is a dummy variable, thus s of t is the length of the part of the curve C between the position vectors correspond to the parameter value t equals a to t equals t, as shown in the figure. Now we differentiate both sides of equation 5.1.3 using the fundamental theorem of calculus part 1, namely the equation s of t equals the integral from a to t, the magnitude of the vector r of the variable u to obtain the equation shown in equation 5.1.4. The application of fundamental theorem of calculus, part 1. Please consult your textbook. Let's consider an example. We want to reparameterize the helix given by the vector function r of t with component functions cosine of t, sine of t, and t. With respect to the arc length measured from the point 1, 0, 0 in the direction of increasing the parameter t. So instead of using the parameter t, we want to use the arc length s as a parameter to describe the helix. Let's have a look at the solution. From the previous example, we have the magnitude of the vector r prime equals positive square root of 2. Since the point 1, 0, 0 corresponds to the parameter value t equals 0, namely, if we substitute t value 0 here, we obtain 1, 0, 0, the position vector of the point 1, 0, 0. And using equation 5.1.3, we obtain this integral, which when integrated gives square root of 2 times t. So the arc length is represented in terms of the parameter. Now if we solve this equation for the parameter in terms of the arc length, we obtain t equals s over square root of 2. Therefore, the given vector function of the helix can now be presented by replacing t by using this equation. Hence, we obtain this vector function, now expressed in terms of the arc length, measured from the point 1, 0, 0.